Welcome. In this training video, we will explore a fundamental question for anyone starting in this field. When should you actually use machine learning? We will cover the core principles and prerequisites that determine if ML is the right solution for your problem. Let's get started. Machine learning is fundamentally about extracting knowledge and patterns from existing data. Think of it this way. Traditional programming requires you to give the computer a precise set of rules, like if X, then Y. Machine learning is different. You give the machine input data, and it builds its own decision model by decoding complex patterns and relationships within that data. The machine learns to find connections using statistical algorithms and probabilistic reasoning, rather than relying on preset rules defined by a human programmer. It then uses these learned patterns to make predictions. What is crucial here is understanding the shift from explicit rules to learning based on data. This diagram shows the key difference between traditional software and machine learning. In traditional software, you input data, and the program uses fixed, predefined rules or patterns to produce outputs. The patterns are hand-specified by a human. However, in a machine learning system, the process is inverted. You provide the inputs and the corresponding desired outputs, also known as labeled data to the ML algorithm. The algorithm's job is to figure out the complex relationship and generate the patterns or rules that link the inputs to the outputs. This means the output is determined by the content of the input data, not rigid, preset commands. This learning capability is the first step in deciding when ML is appropriate. Important points. ML shifts the focus from hand-coding every rule to providing data so the machine can discover patterns itself. What did we learn? We learned that ML is about extracting patterns from data to automate decision-making, in contrast to traditional programming where decisions are explicitly coded. So when do we abandon the traditional approach? We use machine learning when designing rules requires too deep an understanding of how a decision should be made by a human expert. If the logic required is extremely complex or specific to a narrow domain, hand-coded rules become impractical. A classic example is detecting faces in digital images. Until about 2001, this was an unsolved problem, because creating a precise set of if-then rules to describe what constitutes a face based on pixel data is virtually impossible for a human. Machine learning overcomes this by simply being presented with a large collection of images containing faces, allowing the algorithm to automatically determine the necessary characteristics needed for identification. This capability to handle immense complexity is a key indicator of when ML makes sense. We are now building upon the first slide's concept by establishing the complexity threshold. If the logic needed to solve a problem is simple, transparent, and well understood, traditional software using fixed rules is usually sufficient. However, if the patterns are too complex, multifaceted, or simply unknown to the human expert, traditional rule systems fail. This is the sweet spot for machine learning. ML algorithms can learn these complex patterns, making them highly successful for tasks like object detection or speech recognition, where manual specification of rules is challenging. ML should be considered when the inherent complexity of the task defeats standard, explicit programming methods. Important point: ML is the optimal approach when the patterns are so complex that they are virtually impossible for a human expert to define manually, such as in tasks involving subtle visual or textual interpretation. What did we learn? We learned that ML is best suited for problems involving complex patterns that cannot be solved using simple, hand-coded rules. We established that ML is necessary for complex problems. But ML is fundamentally a data-driven approach. Therefore, the first critical prerequisite is having the right data. Machine learning solutions are only useful if there are underlying, non-random patterns present in the data for the algorithm to discover. If your data is purely random, such as predicting the next roll of a fair die, ML is inappropriate. Furthermore, your input data must contain the information needed for prediction. For example, if you want to predict a patient's gender but only provide their last name, the necessary features are missing, and no algorithm can succeed. Always think of your data as a table. Rows are individual samples, like an email or a customer, and columns are the features, which are the properties describing those samples. Following on the complexity requirement, this diagram introduces the necessity of data. If you have a complex problem, the next step is confirming data availability. Crucially, merely having data is not enough. You must ensure that inherent patterns exist within that data. If the data is purely random, ML cannot extract knowledge. Finally, the data must actually contain the specific properties or features that are relevant to the target prediction. If any of these conditions fail, no data, no patterns, or irrelevant features, the machine learning approach is not feasible or will simply not work effectively. This initial assessment saves significant effort later in the process. Important point: ML requires the existence of non-random, complex patterns within the available input data that link the provided features to the desired output. What did we learn? We learned that ML is only appropriate if you have existing data, and that data must contain relevant, learnable patterns and features. Once you have data, you must clearly define the goal, which usually means formulating it into a machine learning task. The most common and successful approach is supervised learning. This is where the algorithm learns from input data paired with the correct, desired output known as a labeled dataset. These tasks typically fall into two types. First, classification, where the output is a discrete category, such as predicting if an email is spam or not spam, or which species of flower belongs to. Second, regression, where the output is a continuous number, such as predicting a house price or a stock price. If your problem cannot be clearly phrased as predicting an outcome based on input data, whether categorical or continuous, you may need to adjust your approach or rethink if ML is applicable. Since we need to define the task clearly, this diagram outlines the basic ML categories. The core decision point is whether you have labeled data, meaning pairs of inputs and corresponding correct outputs. If you do, you are performing supervised learning. This approach then branches based on the nature of the output you want to predict. If the outcome is a set of predefined, discrete categories, like dog, cat, or bird, it is a classification problem. Classification can be binary, 2 classes, or multi-class, 3 or more classes. If the desired outcome is a continuous numerical value, like temperature or price, it is a regression problem. If you do not have labeled data, you might explore unsupervised learning methods, like clustering. Important point: for ML to make sense, especially using the powerful supervised methods, the question must be phrased clearly as a prediction task, classification, or regression, supported by input/output examples. What did we learn? We learned how to categorize ML problems, primarily into supervised learning, which requires labeled data and involves either classification or regression tasks. Why do we even build these models? The entire purpose of machine learning is to produce accurate predictions for new, never-before-seen data. We call this crucial ability generalization. The model must be able to generalize the patterns learned from the training data to future data. We cannot evaluate a model using the same data we used to build it, because the model could simply memorize the answers, which tells us nothing about its performance on real-world inputs. If a model achieves perfect accuracy on the training data but fails miserably on new data, we say it is overfitting. If ML makes sense for your task, the model must fundamentally solve the decision process for inputs it has never processed before. Generalization is the core objective when deciding if an ML solution works. We train the ML algorithm on a set of known examples, the training data, to build the final ML model. This model is then tested strictly on data it has never encountered, the test data. If the model provides accurate predictions on the test data, it means it has successfully generalized and is ready for real-world application. If the model performs poorly, it might be suffering from overfitting, meaning it memorized the training set but failed to learn the underlying patterns, or underfitting, meaning it failed to capture the complexity of the data at all. This entire iterative process ensures that we should trust the model's predictions when it is deployed. Important point: a model is only useful if it can generalize well. If it only performs accurately on the training data, it is overfit and unsuitable for real-world use. What did we learn? We learned that a successful ML model must generalize, meaning it accurately predicts outcomes for data points it has never seen before. Once you confirm generalization is possible, you must deeply understand the data itself. You should never blindly throw data at a random algorithm. You need to ask yourself critical questions. What specific question are you trying to answer? And more importantly, can the data you collected actually answer that question? Every algorithm is different and works best with specific kinds of data, so rushing this step guarantees failure. You must also scrutinize the features, the columns describing your samples, to ensure they contain the necessary predictive power. Even the most state-of-the-art model architectures perform poorly if they don't use a good set of features. Understanding your data is often the most important piece in making a machine learning approach work well. This diagram outlines the crucial steps before model selection. Starting with a clearly defined ML question, you must first spend time understanding the dataset you are working with. If your data is insufficient or poorly understood, you must inspect it and potentially acquire subject matter expertise to proceed. The next check confirms that you have extracted relevant features that possess predictive value. If not, you return to the time-consuming but essential step of feature engineering, which involves creating derived features or pre-processing the data until it is suitable. Blindly applying an algorithm without this foundational understanding of data and features rarely leads to an accurate model. Important point: ML success is often determined less by the choice of algorithm and more by the quality, relevance, and representation of the input features. What did we learn? We learned that ML is only sensible if we spend significant time understanding the data, ensuring features are relevant, and matching the right data type to the right task. We must check if the ML solution is actually practical and needed. Despite the excitement, ML is not a magic tool that solves everything. If the underlying pattern linking input to output is simple like sorting states by zip code, you should use a traditional lookup table instead of building a costly ML system. ML must be both necessary and cost-effective. When starting out, it's wise to begin with a simple model, such as a linear model or nearest neighbors, to establish a baseline performance before investing time in complex algorithms like neural networks. Finally, consider the large context. How will this ML component integrate with the rest of your system? If deployed, production systems demand reliability, speed, and low memory usage, which complex models often struggle to deliver. This flow helps confirm the contextual fit and necessity of ML. After identifying a problem, the first check is complexity. If the pattern is simple, traditional rules are often the superior and most cost-effective approach. If complexity dictates ML, start by trying a simple ML model, such as linear regression, to set a baseline. Before committing further resources, you must evaluate if the incremental performance gains provided by ML are worth the investment in infrastructure, maintenance, and complexity. In short, is it necessary and cost-effective? Only if simple solutions fail, and the gains warrant the complexity, should you proceed to develop and deploy more advanced ML systems. Important point. ML should only be chosen if the problem is too complex for simple rules, and the expected benefits outweigh the increased cost and complexity compared to traditional or simpler ML solutions. What did we learn? We learned that ML is not inherently the best solution. Simple non-ML solutions or linear models should be tested first to ensure cost-effectiveness and necessity before advancing to complex models. Let's summarize the key conditions for when machine learning makes sense. First, you must confirm the problem is complex enough that human experts cannot easily define the rules. Second, you must possess sufficient, quality data containing all the necessary features to inform the prediction. Third, the goal must be clearly structured as a machine learning task, typically classification for discrete outputs, or regression for continuous numerical outputs. Fourth, the resulting model must successfully generalize its learning to make accurate predictions on new data it has never seen before. Finally, before moving to production, ensure the complexity and cost of the ML solution are justified by the predicted performance improvement over simpler methods. This diagram provides a final checklist for evaluating ML feasibility. Starting with the core need for complexity, each diamond node represents a critical check. Does the problem involve patterns too complex for traditional rules? Is high-quality relevant data available to train the model effectively? Is the problem accurately framed as a classification or regression prediction task? Is the goal to generalize and predict accurately on unseen future data? If all these conditions are met, the final crucial step is justifying the increased complexity and cost of the ML system compared to non-ML alternatives. If all checks pass successfully, ML makes strategic sense for your specific problem. Important point. ML should be a deliberate choice based on complex problem requirements, strong data foundations, clear objectives, and guaranteed generalization, ensuring it is the optimal and cost-effective solution. What did we learn? We summarized the 5 key conditions that must be met to confidently conclude that machine learning is the appropriate choice for a given problem.